So in this video, we're just going to conceptually discuss how to find the area between two curves. So the idea is, suppose we want to know the area between two curves, f of x and g of x, where f is greater than or equal to g of x, and we want to find the area between the two curves over some closed interval from a to b, or in other words, between the lines, the vertical lines here, x equal a and x equal b. So if I were to shade in that area, it would be this area right here. Suppose we want to know the area between the two curves bounded by lines x equal a and x equal b. So there's a couple ways that we could conceptualize how to come up with that area. One way would be to use what we've already learned from calculus, that when we integrate, say, the function f of x here, when we integrate f of x from a to b dx, that we are finding the area under the curve, and it's a signed area. So if f of x is above the x-axis, that area is positive. If f of x is below the x-axis, because f of x represents the height of the function, then we would get a negative signed area. So if we wanted to find the area between f of x and g of x, one way that we could do it is just find the area under f of x, which is the highlighted region that you see right here, by calculating the integral from a to b f of x dx. And then what we would want to recognize when we calculated that area is that we would be picking up this region right here underneath the function g of x. And that region isn't included in the region between the two curves. So it'd just be a matter of calculating that area separately and then subtracting it off. So we could integrate from a to b and calculate g of x dx to get the area underneath g of x, and subtract that area off to get the area between the two curves. And of course, if the bounds of integration are the same and f of x and g of x are both continuous over those bounds, we could rewrite this as a single integral if we wanted to. We could take, hey, this is the function f of x minus g of x dx, which could also be written as the integral from a to b of f minus g, the difference of two functions of x dx. So that would be one way to think about how to get the area between the two curves, probably the simplest way to think about it. The other way we could think about it is to say, hey, let's take the region from a to b and cut it up into n rectangles of equal width. N rectangles of equal width. So we take this and we just start hacking it up into rectangles. And then we'll add all of those rectangles up to estimate the area under the curve. And if we do that, we can draw one rectangle that we use to just represent generically all of the rectangles. We could say, call this kind of the characteristic rectangle. This is the ith rectangle on the interval from a to b. And the center of it right here would correspond to x sub I, the ith input value. And what we would want to recognize then is that if we wanted to calculate the area of just the ith rectangle, we would need to know this length, but that distance, but that distance would just be the upper function minus the lower function. So I could say, hey, I'm going to take f and evaluate it at x sub I, and I'm going to subtract from that g evaluated at x sub I, and that will give me the height of that rectangle. And then to get the area of this rectangle, you would need to multiply it by the width. And the width is just delta x. So you would say, hey, I'm going to take the height times the width of the ith rectangle. And then to estimate the area between the two curves, you would just add them all up. You'd say, hey, I'm going to take the sum from I equals the first rectangle to the nth rectangle if I've cut the region into n rectangles. And then you just play off of what we've done in calculus already, and you say, hey, if I want the estimate to become the exact area under the curve, what would I need to do? Well, I would need to fill this region with infinitely many, infinitely thin rectangles. So I would need to take the limit of this estimation as the number of rectangles I was using to estimate it goes to infinity. So this fills the region with infinitely thin rectangles, and instead of the approximate region, we get the exact region. And then based on what we've already done, we know that once we take the limit as n goes to infinity, that we're going to represent delta x with dy instead. And the summation notation, we're going to use the integration symbol to recognize that we've taken the limit as n goes to infinity to get an exact area. And we're going to run that calculation from a to b. And it's going to be the f of x minus g of x, because all possible x inputs are going to be put in over that interval. And instead of delta x, when delta x becomes infinitely thin, infinitesimally small, we represent delta x with dx. So that would be another way to think about how to find the area between two curves. In this box here, I'm not going to read it. It's just a summary of what we've been talking about so that you can put something into your notes to have as you work through the homework.